So hello and welcome to the week 6 of the course where so we are now in week 6. We have covered the material until week 5. So in this particular week we will start with looking at this ISO 14040 terminology. Again, we have covered this ISO kind of in the methodology in the past, but this is just a kind of a recap of the different technologies, terminologies that we have used, and we will go one by one and give you some examples of that as we make progress. So let's look at this terminology one by one. And so first one, we talked about this life cycle inventory. We already spent quite a bit of time on LCI. So what is LCI? Again, this is more like a recap for you. Now whatever you did in terms of part of week 3, 4 and 5 in terms of LCA methodology at the beginning of this week 6, we are trying to recap so that things get fresh in your mind. So in terms of the LCI inventory, we are looking at phases of LCA involving the compilation and quantification of input and output. So these are all the phases of LCA for a product throughout its life cycle. So that's our LCI part, life cycle inventory part. Then we also already kind of looked at life cycle impact assessment, which is the phases of LCA aimed at understanding and evaluating the magnitude and significance of the potential environmental impact. So that's phases of LCA. So what we did in terms of LCI, very similar, very simple. We looked at all the input and output. We made a big list. We had several tables which you saw. So that's our LCI phase. Impact assessment, once we have the LCI data available, we are trying to understand what are the impact categories associated with that and what kind of environmental or human health or ecosystem impact it will have. So it's the phases of LCA aimed at understanding and evaluating the magnitude and significance of potential environmental impact of the product system and throughout its life cycle. Then just now in the previous module, the last module of week 5, we looked at the interpretation, which is the phase of LCA in which the findings of either the LCI or LCIA or both are evaluated in relation to the defined goal and scope in order to reach conclusions and recommendation. So all these different phases are important, but this is how they have been defined in ISO methodology. So just wanted to kind of re-emphasize on that by putting into this ISO definition. You already have gone through this stuff before, but so you should be familiar with that, but just again how in terms of ISO, how they define this different terminology. Then there are some other terminology like product system. What is the meaning of a product system? Here you have product system as it will entail that you have collections of unit process. You have different unit processes with elementary and product flow. Performing one or more defined function which models the life cycle. So you are looking at the entire product system in terms of so whatever is the unit process that goes into making that product. So compilation of all that is our product system. Unit process is the smallest element considered in the life cycle inventory analysis. So the smallest element that we see is the unit process for which we have the input and output data. So the smallest element as part of the process chain for which input and output data are quantified, that's your unit process. So that's the so there will be several unit processes in a product system, and for all of these unit processes we do the LCI, life cycle inventory. For all of these unit process, when we collect this LCI data, we look at its impact assessment, and for everything that we looked at the impact assessment, we do the interpretation. So they are all related to each other. Kind of it starts from unit process, then to product system, then to LCI, then to LCIA, and then ultimately to interpretation, and where you come up with your recommendation. Some other terminology which you have seen earlier: elementary flow, intermediary flow, reference flow. Again, these are ISO 14040 terminology. We have covered this material earlier as well, but just to give you how the ISO defines it, which is not different than what we did earlier, but this is just how the language is there. So just for your, because ISO methods are important, isn't it? We have to do LCA as per the ISO method. So just gives you familiarity with the ISO methodology. So in terms of the elementary flow, it's the elementary flow which you have the whatever is we have the material or energy flow So this is essentially we have the material coming in or the energy coming in. When I say material, we are talking about any like a material including water. So that's water is there as well. For most of the industrial process, we need lots of water. So it's the material or energy which is entering the system, which has been drawn from the environment. So we are, for example, when you go for material, you are drawing it from the different mines, or from the mines it will go to the metal, like a smelting plant. From the smelting plant will go the product. So as a very primary source are the different mines. So it's materials entering the system that has been drawn from the environment without any previous human transformation. So it's like a basic raw material we are talking about. And then whatever is also that's our input to the system. That's the input to the system. If you remember those boxes we had where we had different types of input, different types of output. Now the output is whatever is the leaving the systems into the environment without subsequent human transformation. So that's, these are very important. Like when we are talking about these, when we say without previous human transformation, that means these are the very basic raw material that you are getting, you are collecting from the mines. So you are collecting from the mines, you have not made any changes to them. Once it goes to a smelting plant, we start making changes to it. So here we are talking about the basic material just coming from Mother Nature in terms of the input parameters. Similarly, in terms of the output parameters, we are looking at the material or the energy that is leaving the system without subsequent human transformation. So just to give you an example, say you had an industrial plant where we had certain industrial wastewater discharge. Now industrial wastewater, industrial effluent, some places they call it industrial effluent, some places we call it industrial wastewater. It can be a pulp and paper industry or any sorts of industry where you have this some sort of industrial wastewater coming in. So as per the rule, as per the environmental protection rules for in any country, you will see that these industrial wastewater, before they are released into the surface water, whether it goes to a lake or a river or any kind of a creek or whatever be the source where it is being, the effluent goes away, it has to go through a treatment plant. And that's most of the very common name is used as affluent treatment plant. Some places they may even call it industrial wastewater treatment plant, because there is a difference between when we say wastewater treatment plant, essentially we are talking about like a municipal wastewater. Municipal wastewater is what the wastewater that is gets flushed in our toilet. So that's predominantly those municipal wastewater, and those treatment plants are called they are called STP, like a sewage treatment plant, because that's the sewage material that is there. But on the other side, when we have this industrial wastewater, we call them affluent treatment plant. That's called ETP. So these ETPs, so when we are talking about this emissions going into the environment, so if you think about this water-based emissions going into the environment, we are saying that without subsequent human transformation. So what does that mean? That means that after it has been treated, so your wastewater from the industry, as per law, cannot be discharged directly into the atmosphere, directly into the land or to the water body. So what you are doing, you are treating it in an ATP. You are supposed to treat it. So as an industry, we are supposed to get the treatment done. So it will be taken to a effluent treatment plant. Affluent treatment plant will have different processes and other things involved to treat it, and then the affluent of the treated affluent from this affluent treatment plant needs to be disposed in some sort of water body, or maybe potentially reused back into the system too. So if it's reused back into the system, then again things are not going out. So it's not, but part of it which is going out, either in the water phase or in the semi-solid phase, because you may have some sludge as well, which is produced as part of the ETP. So those things which will get disposed, and after you dispose it, we are not going to do any changes to it. So that's what they are talking about, that without subsequent human transformation. So in both the cases, elementary flow actually relates to the material and energy coming into the system, or you coming into the unit processes, where whatever is the material is coming in, that has come directly from the nature without previous human transformation. Whatever is the material going out, is that going out after whatever treatment has been done, but after it has been released, there is no further human intervention in terms of the transformation. So that probably it's a, if you have if it was not clearer in the previous module, it helps you get clearer over here. So that's what the elementary flow we are talking about. Then we have intermediary flow. Intermediary flow, if you remember when we are going over that unit process concept, we kind of talked about that as well. Here it's basically that's the interaction between the two different unit process. So for a product system, as I said earlier, you may have multiple unit process going on. So in between the unit process there will be some flow. So like a input output from one particular unit process becomes your output from one particular unit process becomes input to the next unit process. So that's your intermediary flow, where things are, so we have the product, material or energy flow which is occurring between the unit process of the product system. So it's not only it is what is being interaction between the different unit processes within the system. So nothing is coming from outside here, it is the things how it's being used up within a particular system. So that's your intermediary flow. Then we also talk about a reference flow. Reference flow is based on measures the output from process in a given product system required to fulfill the function expressed by the functional unit. So remember when we were doing that bulb example, when we were looking at those bulb example, we had with the function, we choose the function as lightning, we choose the functional unit as 700 lumens of light for 10,000 hours, and then we had we said that to achieve that particular function we need 10 bulbs of one type and 1 bulbs of the other type. So there our reference flow was those 10 bulbs of incandescent versus and 1 bulb of CFL. We were comparing those two systems in that particular LCA exercise. So that's the reference flow. The reference flow is of it's a measure of the output from process in a given product system which is required to fulfill the function. So the function in that our bulb example, to require to fulfill the function of giving us 700 lumens of light for 10,000 hours, that we needed 10 bulbs of incandescent and 1 bulb of CFL. So that's where the functional unit functional unit was 700 lumens for 10,000 hours. But to fulfill the functional unit, we needed 10 bulb of incandescent and 1 bulb of CFL. So that's 10 bulb of incandescent and for say product A, product C, incandescent bulb, and 1 bulb of CFL for our CFL system. That would be called as the reference flow. So all the calculations that we did, if you remember from that bulb exercise, was based on those 10 bulbs and 1 bulb. So that's how I did not give you the detailed calculation on the 1 bulb side. We did a detailed calculation for incandescent bulb. For the CFL, I just gave you I just showed you the results. So if you I hope that it was clear. We did not, because for the benefit of time, we did not. It is the same. It's essentially the same way the calculation is done. But again, just to I think I may have forgotten to mention that, but in that particular module, but the detailed calculation was never shown for CFL. We showed it for incandescent, but the same method is used for CFL as well. But we did look at the results of both when we compared CFL and the incandescent bulb. So that's the reference flow. That's the concept of the reference flow. And then we have also has different impact categories. When we say impact categories, there are different types of impact categories. You looked at the long list of impact categories. Climate change was one of them. We have acidification, eutrophication, land use pattern. Some I think there was some other stuff in there as well. So the impact, there are different impact categories. And so that's one example. One of the predominant one we keep on using is the climate change. So that's also is there. Then there is the LCA result. In terms of the LCA results, we always try to put them in the form of amount of a greenhouse gas per functional unit. So we always put things as a per functional unit so that we can compare the different systems. So amount of greenhouse gas, most of the time when we say it's mostly expressed in terms of CO2 equivalent. So it's the CO2 equivalent which we use for our calculation. Then category indicators, we had the infrared radiative forcing. That is one thing because of the climate, for the climate change part of it, we use the infrared radiative forcing, which is the watt per meter square. So that's one example that is that's the category indicator we use. In terms of model, there is a IPCC model. That's the IPCC model, as we know, based on the climate change. That's the model most of our climate change calculations are based on. There are different kind of, if you remember from the table we had in one of the earlier module, where you saw that different type of contaminants or different types of emissions having based on their like a greenhouse gas impact potential for 20 years, 100 years, 200 years. So we use it 100 years for most of the time. So our baseline model is of 100 years of the IPCC. That's where we had for 1 unit of methane equivalent to 24 units of our 24 units of like a CO2. Then characterization factor. Characterization factor in terms of kg CO2 global warming potential for each of the greenhouse gas. That's how we will characterize them. That's kg CO2 equivalent per kg of gas, as I was mentioning to you earlier. You can do a category indicator results. So category indicator results from per kg of gas, you will go to per kg per functional unit, how much things are getting out in terms of the functional unit. So the kg CO2 equivalent per functional unit. Then category endpoints is human health impact, ecosystem impact, and all that. So this is just an example of if the impact category is climate change, how we characterize, how we put these different results, LCI category indicator characterization model. Similarly, if the impact category is something else, we will do a different, again the steps will be the same, but in terms of category indicator and characterization factor, those may change a little bit, but for most of the characterization we express things as a CO2 equivalent. So that's what typically done. So once you have that, you will look at now in terms of the LCA results. LCA results are your outcome of life cycle inventory analysis that catalogs the flow across the system boundary. So you look at the whole elementary flow. Then it provides the starting point of LCIA, life cycle impact assessment. So what is in terms of an example is kg CO2 per functional unit, because LCI, as we have said earlier, life cycle inventory is essentially like an accounting exercise. Any accounting, say if you look at a balance sheet, if you're familiar with balance sheets of company, and when you look at any of the balance sheets towards the end of March, you will see many companies will be start producing their balance sheets, and because for the yearly, in terms of how much sales they made, how much expense they made, what are the different headings under which the revenues were generated, what are the different headings under which certain expenses were made. So similarly here we are doing a life cycle inventory analysis. We are cataloging the flow across the system boundary, elementary flows, and those elementary flows are both input and output of the system. So and taking that information is the basis of doing the life cycle impact assessment, and that is how much kg CO2 equivalent per functional unit. So once and for the impact assessment, we need to know the impact categories. So these are the class representing environmental issues of concern to which life cycle inventory analysis results may be assigned. So we can have life cycle inventory results can be assigned to that, and each category has its own environmental mechanism. So for example, if you look at the global warming, then you have the infrared. We looked at for the global warming, this was kind of impact climate change and global warming. Here the category indicator was infrared relative forcing. LCA results is amount of greenhouse gas. So in terms of global warming, so those were the different ways it is done. If you go for land use, again your impact, some of these parameters will change. When we go for the land use, we will put it in a different way, but ultimately we'll look at kg CO2 equivalent per functional unit, and then we'll look at some of this, whatever is the endpoint. Probably we'll have more endpoint effect in terms of for the ecosystem rather than on human health. So these are how things are kind of basically done in terms of LCI terminology. Some other terminology, environmental mechanism, what are the physical, chemical and biological process for a given impact categories, and either later on in this particular week, if not, then definitely in the early next week, we will look at some of these physical, chemical and biological processes for certain environmental contaminant in the system. So essentially we will kind of do a very quick look at fate mechanism, not that much on the transport mechanism, but mostly on fate mechanism of a chemicals, and how we kind of look how that is important in terms of LCA exercise. So we need to look at the environmental mechanism, which because if you say, we say that okay, this particular, we come up with our emissions from LCI inventory, that okay, this much of certain organic chemicals A or B, C, D, or inorganic chemicals or inorganic compounds A, B, C, D, E, these are being released into the environment. Then the next question comes, okay, what happens when they comes out of the environment? What really impact it is going to have? Say if you had a scenario where there is a industrial processes is out there where certain organic chemicals get released into the environment. Now the question comes, okay, this gets released, but what kind of impact this particular chemical will have? What kind of impact categories we should choose? So that is again, if you remember from the table, there was a long list of impact categories, but which impact category is relevant for this particular chemical? So that's where the environmental chemistry or the environmental, like even the interaction of that particular chemicals with the environmental media, whether it's being soil, whether it's being air, whether it's being water, that comes in picture. So we'll talk a little bit about that in one of the lectures later on, where say if an environmental chemical if it's an organic chemical gets released into the environment, so you have a spill of that chemical, or you had this like a effluent coming out of an industrial plant and just gets released into a soil, on a surface soil, or in a mixture of so now what will happen to this chemical? Will that chemical remain in the soil layer? Will the chemical volatilize and will go into the atmosphere? And what will happen to the chemical, whether it can travel through the ground, through the subsurface, and then hit my groundwater source? So we need to know those kind of answers, and if we cannot know those kind of answers, we cannot really find out what in terms of when we look at the impact assessment in terms of what is the real impact, whether if a organic chemical gets released, but organic chemicals, once it gets released, most of the organic chemicals are volatile. But say if it's not a volatile compound, just for our discussion sake, if it's in the volatility is 0, there is no volatility of this compound. So in the, or you can say it was to make yourself more comfortable, you can assume that it's an inorganic compound, not an organic one, because it's difficult to sometimes when we say that organic compound, first thing comes in our mind that there will be a volatility factor involved here. But say if it's an inorganic compound, non-volatile, so you have now what will happen to this compound? Whether it will stick to the soil, whether it will remain in first few inches of the soil, first few centimeters of the soil, or whether it will go into the subsurface and then it will go to the groundwater. So that's those things we need to look at. So that's where things becomes important in terms of environmental mechanism. So we have to look at this environmental mechanism. We have to try to understand this physical, chemical and biological process, and for a given impact categories, then that will link and then link it to the life cycle inventory analysis. That will give us a results in terms that will give us to category endpoints, what kind of endpoints we are looking at. So when we look at in terms of the indicator, we impact and the other things, the impact category indicator, that's a quantifiable presentation of impact categories. Goal is to reflect all the extractions or emissions, and then for climate change, it's the infrared forcing that we use. Then you look at your characterization model. Characterization model is your what kind of a model you are going to use. You can reflect the environmental mechanism by describing the relationship between the LCA results and the category indicator, and in some cases the category endpoint. You can calculate the characterization factor in terms of what factor you need to use for that. And what is the characterization factor? It's the factor derived from a characterization model which is applied to convert an assigned life cycle inventory analysis result to the common unit of the category indicator. So the common unit allows calculation of the category indicator results. For example, what is kg CO2 equivalent per kg of greenhouse gas emitted. So here if you remember, for the methane we use the factor of 24, for nitrous oxide 298, that's the kg of greenhouse. So how much is the conversion factor? So that's based on the characterization model that we used, is based on the IPCC document. That's kind of the base document that is being used in most of the LCA studies, where based on the ICA based on our IPCC document, we come up with the characterization model. We use 100 years the model, and then characterization factor, we get the numbers from that, and that's what typically get used in the study. Then at the end you will have your category endpoint, which is the attributable or aspect of natural environment, human health, resource, identifying environmental issues. For example, human health impact, ecosystem impact, that could be coral reef, forest, crops. So that's the category endpoint of that particular type of impact that we are looking at. Then you can do sensitivity analysis, uncertainty analysis. So we kind of talked about that earlier as well, so I'll kind of not spend too much time on this one. Sensitivity analysis, you're trying to say whether what is the methods and estimate the effects of choices made. So you keep, say if you have 5 parameters, keep 4 constant, vary 1 and find out. Uncertainty gives you in terms of the model impression inputs. We talked about that in earlier model, data variability, model imprecision, inputs are uncertainty, those things are there. Critical review is once you have processes intended to consistency between a life cycle assessment and the principle and requirement of international standards on life cycle. So you need to kind of make sure that whatever things we are doing is as per the and international practice. So it's that's what it's kind of talked about in terms of the critical review of the entire material. So these are some of the ISO terminology. Again, most of these material we kind of covered earlier. So this was just to give you, again, this definitions came directly from the ISO document. So just to give you how the, although I have told you that you should try to get the 2006 copy of that ISO document, but just in case if you don't even have the copy, you should be able to understand what are the different terminology that ISO uses. And that if you get the ISO document, that's a several page document. So and here it's what we have provided is a summary of that. So I'm not saying that you should not, actually I'm encouraging you to get hold of that ISO document and look at it. But and then once you read it, if you cannot understand, this particular video will help you understand that ISO document. And but if you need to, other than ISO document, you should also read other stuff. So there are towards this particular we have listed some sources where you can get other information from different sources, and these are again some of this information, and this list is a little bit older. There could be newer informations out there as well. So but this is, at least if you read this will give you a good idea about whole LCA procedure or LCI procedure, that is how the LCA is done. So with this we kind of come towards the end of this LCO methodology stuff. Now in the next module I will quickly give you what are the good points of an LCA. So we have already told you that how the LCA needs to be done, how will you interpret the results, what are the different what are the ISO methodology, ISO terminology, and everything we have taken care of that. Now in the next module I will try to give you that if you are going to do a LCA exercise, what are the key points, kind of a summary of the whole LCA methodology. What are the things like do's and don'ts? I will give you, we'll try to go over that, and then we'll start looking at some of the other material in terms of many things that we talked about in this LCA methodology. We'll try to explain them in more detail. Like one thing, if you remember, we talked about this environmental fate, like a pollutant fate mechanism. We'll cover that kind of stuff in subsequent modules. So with that, let's wrap this particular module, and then we'll look at key points of a good LCA in the next module. Thank you.